everyone, and welcome today back to Activity 9. Today we're going to talk about Lesson 9.2 and looking at different features of our polynomial functions. Now, before we get started talking about the graph features, let's talk about a couple of important vocabulary terms. First and foremost, we have the end behavior, and that's what's happening with our graphs as our x values are getting bigger, going towards positive infinity, and as well as our x values as they are going towards negative infinity and getting smaller. What is happening there? What's going on with our y values? Are they going towards positive infinity, negative infinity, going towards a value? You will see a lot of that today. We also want to talk about things on our graph like our x-intercept or the zeros where we touch the x-axis, y-intercept where we touch our y-axis, and our amount of turning points, either our maxes, our relative maxes, or our relative mins. Those are our turning points. We also can talk about the intervals in which our graph is increasing. So as we move left to right, are we going up on the roller coaster hill? Or as we go left to right, are we going down on that roller coaster hill? The different intervals in which all of that is happening. So we talk with these polynomial functions with their overall highest degree, and they usually like to write them in nice descending order. Again, and we talked about some of these other vocab words with end behavior and then increasing versus decreasing. So now we see on page 124 these different graphs, and we want to talk about these different important features of the graph as they pertain to what they gave us. So first things first, let's look at the domain and the range. Well, for both the domain and the range this time, it's just going to be all real numbers. There's no breaks in our graphs that we have to worry about. Our y values are going from negative infinity all the way up to positive infinity, so all real numbers. And as we look at our end behavior, as our x values are getting more and more positive, so as our x's are increasing this way, our y values are going towards positive infinity as well. They're getting really, really big. And then if we analyze what's going on with our values as our x's are getting smaller, well, so are our y values. So we would say as the x values are getting smaller, going to negative infinity, so are our y values this time. Our x-intercept on this graph, if we check out where we see some of these zeros, our zeros are happening very close to -4, very close to -1 it looks like, and just before we get to 2. So we're just going to kind of estimate on this one. So our x-intercept, or again the zeros this time, are going to be at x equals about -3.8. We could say on this graph, -1, and then just before we get to 2, so like 1.8-ish on that particular graph. If we look then at our max and our min, we have this max point here at about -2.6-ish. If we just, again, are kind of guesstimating off the picture of the graph. And then that's all the way up a little over 8, maybe 8.7 just before we get to 9. We also have what we would call the relative min here, where if we look, we are at about 0.6, and then about a y value of -8.7 would kind of be that point that is the smallest on our graph. Now, our increasing and our decreasing intervals, we can look again kind of as we go from left to right what's happening here. So we're riding the roller coaster up is basically our increasing interval, right? So from negative infinity until we get to that max point at about -2.6, we're going up. We're also going up when we are at that min point of about 0.6 until we get to infinity. The decreasing interval then is in between there, right? The decreasing is coming in between that max and that min point. So we would say from about -2.6 to about 0.6 at that min, those x values is where our graph is decreasing. Now our next graph then here is a cubic, right? We have a third degree polynomial, and our domain and range on this one are going to start off as all real numbers again for both pieces, right? Domain is all real numbers, range is all real numbers, nothing getting messed around on this one. And our end behavior, similar to the last graph, as our x value goes to positive infinity, so does our y value. As the x value goes to negative infinity, so does our y value. So again, we see that opposite nature. Now this time we only have one x-intercept, or 0, and this time that's occurring at the x value of about -1. It looks like it's kind of on that point. Y-intercept this time is also at 1, or you could say 0, 1 for that y-intercept. And this time, it's interestingly enough, we're actually increasing the whole time. We never actually take a point. There's no maxes or mins. So we would say we are increasing from negative infinity to positive infinity on this one. They're just kind of going on forever and ever and ever. Now there are two more graphs that are kind of similar in nature. Now the biggest switch on this next cubic that we're going to notice is this end behavior. Okay, this time when we look at our end behavior, as our x's are getting bigger, our y values are going negative, versus when our x values are getting more negative, our y values are actually getting more positive. So we kind of see that opposite nature. But otherwise we still see, different increasing and decreasing intervals. This time with our cubic in the next example as well, we still see that opposite end behavior, that decreasing as x's are going in positive infinity, the y's are getting more negative. This time though, we have very tiny little maxes and min points, and we can see, that in there, and then again our little increasing, decreasing intervals. Now, what is some of the features then that we're noticing about these end behaviors as we look at these graphs? Well, any of our graphs that are quadratic, right, or cubic, so quadratic, quartic, aka any of the even degreed polynomials, okay, they are going to have the same end behavior. What do I mean by that? They're either going up both directions or down both directions. So again, they're specifically saying the quadratics, but this is going to work for your quartics, your even degrees in general. Your end behavior will be the same. So as x goes to positive or negative infinity, your y values will be the same, either both positive or both negative. On the other hand, our cubic graphs, or maybe your other odd degree polynomials, they're going to have opposite end behavior. So what do we mean by that? Well, okay, if we look at some of these cubics, they either going up like this or down like this. So as x goes to positive infinity, the y is going to be doing something. Well, we know the negative infinity will be the opposite of that. So if y is going to positive infinity here, we know that because of that opposite nature, it would go to negative infinity there. Or if we're going to negative infinity up here, this has to be positive infinity. Again, it's going to be opposite in those y values, regardless of that. Now, either way with these, though, what's something that we can kind of compare, that leading coefficient is going to dictate some things. What do I mean by that? Well, the leading coefficient, if it is positive as x goes to positive infinity, so will our y value. But if our leading coefficient is negative as x goes to positive infinity, our y value is going to be negative infinity. Okay, so that's going to dictate what happens on this right-hand side of the graph. And we can see that here. For instance, we have this negative here. This went to negative infinity to the right. Negative here, negative infinity to the right. But these graphs up above that were positive inside of here, so positive, going positive, positive, going positive. Right. Well, we can also, again, use our graphing calculators to look at some of these different pieces, the degrees, the leading coefficients, what's going on with our end behavior, max number of zeros, max number of turning points. Now, some of these we are not going to necessarily even need to look at the graph, but it can kind of decide for us some of these things just to confirm. So notice on this first one, our degree here is 2. This is an even degreed polynomial. Our leading coefficient this time is a negative, right? In this case, a negative 1/2 is our leading coefficient. The max number of zeros is going to be the same as your degree, so 2. The max turning points then is going to always be 1 less than that degree, so 1. And we know that as x goes to positive infinity, because this thing right here is negative, that means our y values are going to go to negative infinity. Now, on this one, as x goes to negative infinity, because this degree was even, we know that it's also going to match and go to negative infinity. So what we can do is kind of confirm. So I typed in that graph. I'm going to zoom 6 to reset my window. And I see that quadratic, right? Going to negative infinity. We have max of 1 turning point, max of 2 zeros. And we see that end behavior works out to match that. Our next one we're going to look at is letter B. This time, don't be fooled by the number where the degree is happening. They don't have it in that expanded notation. This time, our degree is going to be 5 because we have x to the first, 2, 4 more for a degree of 5. And our leading coefficient, notice out front here, is just a positive 1 in front of that x. We don't see any negatives to worry about that leading coefficient. Our max zeros is going to be then the same as the degrees. The max zeros is going to be 5 this time. The max turning points then is 1 less with 4. Again, that's just the max number. This time, as our x goes to infinity, because we had this positive leading coefficient here, our y values will go to positive infinity. And because this is an odd degree, though, as our x values go to negative infinity, this is going to be an opposite symbol. It'll be negative. So we can, again, consult our calculator this time to kind of check out some of those features. If I select this and I look at my graph this time, we see that we have our max number of turning points, and then we see this end behavior, especially x value this time going up, y piece going down as the x's are getting more negative. All right, our next one on our list, we're going to skip letter C. We're going to talk about letter D this time. And letter D is in standard form. Our degree is 4, which means that is also going to be the max zeros is also going to be 4. And our leading coefficient is negative. It's negative 2. Turning point maximum is 1 less than that. Max zeros, we're going to have max of 3. This time when we check out as x goes to infinity, because again, we know that this leading coefficient is negative. This is negative. And because our degree is even, this is going to have to match because this is an even number. Our y values are also going to be going to negative infinity. So again, if we select and kind of check out this graph, we see that happening. Both of these going towards negative infinity, and then the max of 3 turning points this time showing up on our graph. All right, last one is going to be letter F. Try that out. Okay, you should have seen on letter F, if you check out its graph, or just looking at the function, we have a 5th degree polynomial, so a max of 5 zeros. Not necessarily going to have that, but that would be our max. And leading coefficients negative, so as x goes to positive infinity, y's are going to negative. As our x's are getting smaller, our y's are getting bigger on this one. Max zeros again is 5, and that means our turning points are 1 less than that. So officially would have a max turning points of 4. Now you might be asking yourself, and this is our last question here for the day, but how does our number of roots affect things? Because notice on some of these, we said, for instance, on this one, that our max number of turning points is 4, but if we actually go back to the graph and look at the graph for 2, we notice that it actually doesn't have 4 turning points, okay? We might be bouncing less, or we might not have the max number of zeros, right? Our max number of possible zeros this time was 5. This time we only see 3 on here. Well, why is that happening? Well, it goes back to the idea of a double root. And what a double root is on our graph, when we are touching in more than one spot, we have a max or a min at the 0, that's going to be our double root. So we see on this particular function, again, a max or a min at a 0 or x-intercept, that's going to be our double roots. And what it does is it can affect the number of zeros we see, and that's why we always call them the max number, because that bounds is kind of taking up multiple of them. And we will talk much more about these double roots in class as well. All right. Thanks everyone for watching. We will work more in class.